Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Bedam with Atlanta Functional Programming. I hope all you are having a great holiday season. Today is going to be our second to last um, video of the year, which I'm excited. And we are continuing our discussion of paradigms of artificial intelligence programming, case studies in Common Lisp. Particularly, our focus today is going to be covering what we've learned on Chapter 7, which is the chapter that discusses solving algebra word problems. And in particular, we're going to be covering and studying Norvik's code for a program called Student. I thought I would briefly mention some of the historical notes that are present in his book, just so that we are aware of the context in which this particular program was written in. And a couple of lessons that were brought up throughout the actual discussion as I was reading this that I'd like to highlight today, specifically given the fact that Student is yet another language understanding program, much like ELIZA, and in that realm of being able to solve particular kinds of tasks. Okay. Up until now, we've been covering a lot of techniques that are dealing with language in the case of natural language processing and natural language understanding. And a lot of these techniques, even today, could be applied to modern systems. However, it is noted that with techniques like such that has text generation via using large language models, that is much of the widely accepted practice today, given the w- wildly successful ChatGPT and its ilk. It becomes apparent that some of these techniques might be more antiquated to some folks, but I will say that the specifically when it comes to things like student, which is what we'll be discussing today, some of them would end up being optimizations, especially if you know the kind of text that you are actually parsing and specifically how well defined that kind of question is presented to a program such as student. This is very important because when we start looking at artificial intelligence programs, not just in the chat GPT realm and text generation realms that we're looking at today, but even in larger realms when you start talking about dialogue translation and machine translation and so forth, some of those techniques, as far as this presenter is concerned, is could be overkill to the types of problems that you might end up be solving, especially if you know based on the presentation of the problem that a simpler approach could be taken. So I will highlight that as we go on. But first, we need to first talk about what is student. Um, Student was written by Daniel Barbro as part of his 1964 PhD dissertation. Um, and it was a program that was specifically designed to solve the kinds of word problems that one would see inside of a high school algebra textbook. All right. So an example, as I am presenting to you, is the following: if uh, if Jane is twice Bob's age and Bob is three times the age of Joe and Joe is 25, how old is Jane? All right. Anybody can take a look at this and see that Jane would be 150, which means she would be a pretty old individual. But it's particularly interesting how quickly this type of program is actually leveraged. Um, to give an example, like how this is encoded in our student program today, I thought I would start with how um, student was at least implemented by Norvig. This is very much similar to what Barbaro did in his dissertation. It's a complete specification of it. It was actually reprinted in 1968 by Marvin Minsky, who was his then, I believe it was his advisor at MIT. Um, and Norvig kind of went through the original description and implemented it. Although, again, it's not as complete in that of the fact that I believe the original implementation had a natural language actual interface on top of it. Today, we're just going to be using Lisp lists to actually go in, construct the question that would then be parsed automatically. So that way we don't have to incur an additional parsing step in the implementation to actually convert the natural language test that's defined like line 13 into something that can then be additionally parsed and understood and converted into something that Lisp can solve. Um, that said, a couple of notes about Daniel Barbaro because he is a quite distinguished individual for folks who are unaware of his work. After his dissertation, Barbaro went on to working with at BBN, where he actually implemented an operating system called 10x, which was one of the first few time sharing systems. He then went on to Park, where he worked with Warren Titleman, Larry Massenter, and many others on the Intralisp system, which he actually ended up winning the ACM System Software Award, I believe, in the early 90s, along with that team. Barbaro also, I believe, was either involved or was also one of the few people that started looking into the common Lisp object system, although it wasn't the he was more of the what's it the he was one of the people on the actual exploratory group that actually uh, created the actual standard as part of the X3J13 committee. Um, he uh, he was working in cooperation with many others, including David Moon, Sonia Keene from Symbolics, along with um, Richard Gabriel from Lucid, and Craig Kazillis, who many should you should know, has who went on and gave us the uh, Common Lisp Meta Object Protocol that ended up also inspiring aspect-oriented programming. So his pedigree is too much to list it here, but um, I wanted to kind of highlight that a lot of his work is was very much in regards to system design in Common Lisp, and at a time was also focused on a lot of stuff related to AI programming too as well. Although it was more focused on trying to improve Lisp for larger scale software engineering, as you could see with some of his other efforts. So given this word problem that we see here in student, what does his original system do? Well, we can actually look at what uh, how the system looks like if we ended up picking, let's say, let's actually rewrite this student. So you would end up writing in today's in the system that we're going to be code reviewing today, the program like this. So you start with student. Student will take in a list of words. Bob and Bob is 3 times Joe's age. And Joe is 25. Then how old And you could see that it's able to actually end up solving this. What particularly things that you would I wanted to highlight is the equation generator as well as the final solution because both of these are actually pretty important. The equation generator parses the text and actually constructs the actual set of system of equations that will then ultimately solve. And then the solution will then typically get solved based on some basic techniques that one would normally do inside typical algebra, which is, re reworking the equations until you have at least one unknown, and then run the substitution method to actually go and take the known values into it to see if you could solve it for the remaining unknowns that are inside of the system of equations. Um, a couple of things that I wanted to bring up before we begin, which is, as many of you may have already noticed, uh, when we are writing these word problems, particularly word problems that ended up having, like, say, a comma or a period, I was actually using the pipe characters to actually go and escape this comma, or if we ended up using a period, we'll end up using a period. The reason for this is as many of you know, in Common Lisp, comma and period are have significance inside of the Lisp reader. Specifically, when you talk about comma, the comma operator is particularly used for macros to actually unquote variables that need to be evaluated by the Lisp reader at the time of macro expansion. So when the Lisp reader encounters a comma and it actually does not see that comma inside of a back quote, it actually throws up an error. And that error is telling you that it is not using a back quote. So if we ended up using, say, 1 comma 2 here, oops, sorry. Um, let's do it in, see if I can do it here. Let me try uh, 1 comma, no, this is a special character here. Um, Let me try it here to kind of show you what this might look like. If we do 1 comma 2 and we try to get this evaluated, you will see that this comma operator here gives us the following error, comma, not inside of a back quote. And that's because the back quote, as many you know, when you are writing macros, the back quote actually tells the Lisp reader we are starting a potential macro expansion or a macro template that we're going to end up wanting to get expanded upon the invocation of the actual macro. So you're defining the actual template, in which some cases you might use the comma operator to unquote a particular Lisp expression. So that's specifically something that needs to be aware of. The other thing is obviously if you end up using the dot here, this means that it's a dotted pair. So when we encounter it, you will see that it um, will print it as a proper dotted pair here. But if you ended up using, say, this in a sentence, then what that will do is it creates a console rather than actually parsing it into something that should be um, leveraged by the actual equation solver. All right. So let's go and look at how this is implemented. A couple things to be aware of um, in this implementation, one of which is, one second, where is that? Lisp projects, PAIP Lisp. This one, Lisp, good student. There we go. Yes. All right. To begin with, we need to understand that we're dealing with several types of things, right? One of which is there was a specific call out to expressions equations, variables, and essentially typically things that you would normally encounter when you're dealing with algebra problems that I thought I'd actually also call out. Um, so to begin with, we need to make sure that we are representing expressions, variables, equations, and set of equations along with variables in the best way to actually allow us to leverage Lisp to its fullest capabilities. Because again, if we can somehow translate the word problem into something that Lisp already has available to us, then it makes it easier for us to actually just leverage eval in those appropriate cases, so that we don't need to actually deal with additional parsing or creating additional data structures to keep track of the mathematical variables or the representation of the equations that we later on will have to end up interpreting ourselves anyway. All right. So the easiest thing to do is just represent all of these mathematical constructs directly in Lisp. So we'll use symbols to represent variables. We'll use nested Lisp with prefix operators to deal with expressions, and l- and expressions or equations. I mean, both will end up using prefix operations. And We will create a system of equations as being a list of equations, all right? So this is kind of how the system is structured, all right? So what you see here is what Norvig did is exactly that. A couple things to point out. The def struct that he defines in terms of the rule there, he actually ended up defining the rule explicitly has a type Lisp, which will contain a pattern and an appropriate response to that pattern. And That's a pretty typical one that we've actually seen in previous things. As well as in the expression, we actually ended up having an additional structure that has its own explicit constructor. This constructor, I think we've encountered before when we dealt with structures in the past. If not, just a quick overview. You could, in a def struct, instead of having def struct generate a constructor for you, you could just specify your own constructor that creates a constructor expression, and it will be essentially overriding that make dash structure name that typically gets created. So instead of make dash expression, you have mkx to actually create expressions here. This will take in a LA and left hand side operation, right hand side, and all this is doing is rewriting the expression into a prefix form so that Lisp can actually understand it. One thing to point out here in this instruction is if you can actually, if you're actually keen on actually looking at this, it will become abundantly clear what we're effectively doing here is implementing the rule structures to create a rule-based translator like we did with Eliza. Um, this technique once again pops its head into our sort of tool shed, which is taking a rule and translating it into a form that we can actually understand. So you don't need to necessarily do a lot of work in terms of parsing your text if you actually have your text written in such a way that allows us to just simply do a substitution where we extract the variables that we want to extract from the expression, and then we rewrite that expression in such a way that we would uh, evaluate it later on, particularly when we run what uh, the actual solver to actually solve the individual equations. So let's take a look at how these rules look like given this structure here, right? Shall we? Again, predicates and stuff, I don't really need to actually go through and explain that one to you. This is our pattern match and abbreviation for 0 or more instances, and then we have our database here. Um, so our database for rules, our database of rules, which is what I'm calling this structure here, is literally just doing a pattern matching abbreviation expansion on the individual rules written in this pattern response form. And what this will ultimately do is create the appropriate expressions that we'll end up using in the solver later on. Um, so given this particular rule, all right, immediate things that most people will end up probably recognizing is that these, when you design rule-based translator like this, much like ELIZA, if you end up using similar structures, all right, so that is sentences that provide the same exact meaning but are worded in a way that doesn't match any of these specific rules, you will end up creating a word problem that cannot be solved by student, mainly because of the fact that it does not recognize the particular words in your word problems. And we're going to actually go back and adjust some of this stuff because this is something that I actually got hit at earlier prior to actually presenting this, where when I was trying to set up the word problem, the simple word problem, than the one that was in the book, I ended up encountering one of these rules, and I didn't want to actually go and change the rule database until we actually covered it today, just to show you that once again, it's just a simple pattern expansion or pattern matching that you can actually use to actually go and extend student to actually solve particular type your particular type of word problems. All right. Um, Once this is in, then we have the actual main program, all right, which actually calls solves equations, which is the main thing that we're going to actually look at. The create list of equations essentially is using the rule database that we have to actually translate our each of the individual words that we created into an expression and then generate a list of equations that we could actually solve later on by solve equations, okay? So if you look at this, all this is doing is it's creating a list of equations using a set of expressions. And then this expression is coming from this rule translator that takes a set of words, and if that matches one of the particular rule patterns, just like before, we ended up creating the translate pair bindings with the actual response that we've encountered, and we run substitution on it to replace those special variables that we created, represented by the question mark, with the actual word that we want to actually solve. And you saw that earlier with the basic example that I've presented. Once this list of equations is generated, which looks like what I showed you earlier, okay, so you end up generating this list of equations, but internally, so this print equations is actually taking the list of equations and converting it in from prefix form into infix form, okay? I'm going to show you print equations later on because that actually formats this so that you're aware of what it does. But the main thing to note is that internally, just take those infix equations and then just flip them into the prefix form, and you have essentially the same set of equations that create list of equations is actually creating. So let's go and talk about the solver. What? Wait a second. There we go. All right. Before I begin there, I'm just going to pause for just a minute and see if there are any questions from any folks. Please note, these are just discussions. I don't want to lecture about this chapter, but so anybody who has a particular question, by all means, please write your question in the chat window, and on anything Lisp related or any of the stuff that we've encountered thus far, and I will answer them accordingly. All right, looks like there are no questions, so let us go and look at this solved equation, shall we? Solved equations, please ignore the print equations for a minute here. Essentially just prints out the equations that we just created from create lists from equations, but more importantly, it ends up then solving them using a technique that I've already mentioned to you called constraint propagation. The simple thing about constraint propagation, everybody learned this in high school, right, is just figure out one of the equations with one unknown, substitute its value into the others, and then solve the equation, the remaining equations, one variable at a time. All right, one unknown variable at a time. And if you stop, you when either there are more variables that are unknown than are known, and you can't actually solve any further. In which case, what student does is it will actually go and retrieve um, what is known, and just return that. So I gave you an example of when everything is known, but let's simply change student here. This same word problem that I created just ever so slightly to show how constraint propagation fails when there are more unknowns than knowns, all right? And all you have to do for this is simply change this to, say, thrice, all right? Which everyone knows is three times. It's the same thing as saying three times the age of, okay, and thrice, if you write thrice like this, what you end up actually is you've changed even though you didn't change the semantics of the word problem, it's the same exact word problem. Student will not understand this and end up creating the following set of equations that it actually creates. So this is just illustrating the point, and this is something I will actually extend, because this is really nothing more than a simple extension of students, the rules here, where we have twice here. We could just create a thrice. Okay, reload the database, rerun this, and we'll end up getting the same problem. This isn't really that big of a deal once you actually know how to extend the database. All right. So how does the solver work is the big question, right? And how does constraint propagation actually work? Um, so let's us look at this for a bit and dissect it. Okay. So for the majority of the problems that we're encountering with student in this first problem, a lot of them, since you're dealing with algebra, we are restricting ourselves to probably the basic arithmetic operators. Okay, so we're talking about it's not full PEMDAS for most of you who remember what PEMDAS is: parentheses, exponents, multiplication, division, addition, and subtraction. We are focusing mainly on the latter part. We don't deal with exponentiation or parentheses. We're only dealing with multiplication, division, addition, and subtraction from left to right. And what solve arithmetic does is it actually takes in something that's already been predefined in the particular um, arithmetic form, and then as the name indicates, solves it, right? But the bigger question is what this isolation function does. This isolate equation x, all right? So given a particular equation, what it does is it calls one unknown to figure out what um, if there is exactly one unknown in the particular expression that we are dealing with. All right. So this is a recursive function that checks to see if the expression is unknown, and if the unknown expression isn't that's usually a contain function that just check to see if it's a symbol. All right. Then we have nothing to kind of worry about. If it's an atom already, then we know that it's already um, we know that it's not a unknown expression, so we then return nil. Otherwise, we go and check both the left hand side and right hand side to determine whether or not there's exactly one unknown. All right. Given this one known expression and we figure out the unknown that's in that particular equation, then and we know that it exists, more importantly, which is why we're using the when form, then we try to isolate that. And what that isolation is rewriting the equation with the single unknown variable in a way that it can be solved. Okay. There are about 8 cases when you're dealing with this. Okay. I think 5 of which are written here. I don't believe the other ones are there. So, but the book illustrates that there are 8 cases for this, and mainly it's because of the fact that um, in the simplest case, x equals n is important. Then that's the simplest one. So like if it's some sort of known variable that's equal to x, then we just return it. We saw that with the example of Joe. If I say Joe is 25, Joe is our unknown. Joe equals 25 will then become the expression that got created for this particular example here. Case 2 and all the other ones are dealing with the arithmetic operations. Addition and subtraction has I hope most of you remember from your arithmetic classes, are commutative operators, which means a plus b equals b plus a. Um, and so case 2 and 3, when you're doing a plus b or a times b, will essentially deal with both of those. And so what this is doing is it goes through and rewrites these expressions so that they fit in these other isolated cases, and it creates, more importantly, the correct left-hand side and right-hand side of the equation once it's been rewritten. All right. Um, and you could see right here, we could where we're checking commutativity in order to deal with the commutative cases, and then we handle the other cases explicitly, and specifically by other cases, we're talking about division and subtraction, where you have to actually move around the variables until the equation actually hits a form that's canonical. So I encourage some folks to actually go sit down and actually deal with some of this stuff a little bit, like looking at it, what this is. I will try and show you some of the ways this is actually implemented. But if folks are interested in a more deep dive and actually figure out how it's rewriting this, let me know. The main thing is operators and inverses. What this does is the inverse operation is using the structure op that was created. So remember, we created a struct called that represents an expression that holds the ops explicitly, and what it does is it will actually go and use that associative map to actually go in and look up the inverse operation to change the equations. So that's exactly what case 4 is doing when you're dealing with commutative operations. So when you're dealing with plus, it becomes minus. When it becomes if you're dealing with times, it becomes divide, and so forth. For the cases where we're dealing specifically with divide or minus, we have the fourth case where it actually goes and calls recursively isolate on the expression, where we are rewriting the expression in such a way that in a form that will allow us to actually go in and uh, re-isolate, so to speak, the variable once we've moved. So and the example here that you could think of is for um, a divided by f of x. What it has to do is it has to first construct a new expression where the right hand side is now the left hand side. I'm and the right hand side of the expression becomes the left hand side of the expression that you're going to try to solve. All right. And then the right hand side of this new expression will be the rewording of the actual operation that we're attempting to do. So in this case, what we'll do is left hand side of the expression is divide. All right. So we took f of x here. So the right hand side of the left hand side is b here. Okay. So if we take this expression, which is, so this is a divided by b. So we took the left hand, the a divided by f of x, and then what we did is we took the right hand side of that expression, which is now we're dealing with the divided by the f of, so we're now dealing with f of x, because remember, a divided by f of x is itself an expression, right, which will contain a left-hand side and operation and right-hand side. So the right-hand side here is f of x equals, and then we took a here, so we took the left-hand side of the left-hand side. We took the operation of this, which is divide, and then we provide the right-hand side of the expression e, which is b. So this is already doing the rewrite for us, and then we're running isolate again to see if we need to run it another time. So this recursive expression at some point will design a single expression that contains a single unknown that can then be used by solve arithmetic to actually go in and run the evaluation. All we need to do now is once we have a form that we have a couple of unknowns for, we can actually run an eval against it, because the expressions are dealing with two two known values. So that right hand side will be completely substituted. All of the values on there will be fully substituted, and we could then just make a single expression that tells us, well, based on this evaluation, this means that this is equal to that. So through just a simple rewrite of our natural language equation, okay, which is our set of equations here, we were able to construct a form of equations that can be solved using constraint propagation and we can just run evaluation once a single value is known to trigger essentially like a signal every other known equation up until all the equations are solved, and then we end up returning this. So um, that's actually student in a nutshell. There really isn't much about this that I need to go through because it is pretty self-explanatory in terms of how the solved arithmetic is solving this. Um, I encourage you to to dig in this particular right-hand side feature more. We will be covering the word problems that I just kind of evaluated to kind of show you to what extent you are dealing with, and hopefully that would give you some more understanding on how this system works. But the real goal and the end lesson that I learned from reading this is rule-based translation for well-defined problems and well-defined domains can go a long way um, over people just assuming everything is unsupervised learning like we currently do, which is an attempt at trying to dismiss some of this stuff because you have a lot of computing power. And I want to touch base on that when we start talking about neural networks much later on after we cover a lot of the systems that and case studies that PAIP cover. But this is something that I'm going to reiterate as we go through these systems to kind of illustrate that for simpler problems, don't use a sledgehammer. If it's possible for you to solve this problem simply, solve it simply. Don't try to um, don't try to think that this is going to be a larger class of problems. Start it with simply and then extend it up until you really need to leverage um, that sledgehammer because in many cases you may not need to. You may be able to get really far with what you have. All right. So the one thing I want to point out here is print equations, and then we're going to also touch base on what was the other one? Oh, prefix to infix, which is something that I'm sure most people are um, curious about too as well. I'm going to pause for just again a second here, see if there are any questions. All right. Okay. Last two things that we're going to be touching on. Um, so print equations is a fairly simple, fairly straightforward implementation of effectively a format string that we've actually covered before. Especially for those of you who have been with us when we covered this in practical common Lisp, because this is actually a pretty standard thing to do. So to give you what this is doing is it's printing the list of equations where there's a new line, and then internally it's going to take so it's going through every equation, and for every equation it prints a new line. Then it goes into the equation and it actually goes and prints the equation. So this first thing here is the header, okay? This first A, okay? This is saying begin iteration of list, okay? This beginning left brace. Uh, then before it even prints out the next list item, it prints a new line. Okay. So most people, if you recall, tilde parentheses is a new line. Then it adds a couple of spaces, and then it prints the actual equation, okay, in infix through the the infixed expression is already done through mapcar. So this list is actually already infixed for all of the equations that it's created. And then it will go on to the next iteration. So this closed parenthesis, closed left curly brace here is to go to the next equation to actually go print out. Okay. That's all that this is doing. But the magic sauce is this prefix infix function. This prefix infix function, what this does is again, um, this is a if statement. Basically, if we're dealing with a single atom expression, we just need to simply return it. Otherwise, we're dealing with an actual structure, in which case we have to go through and run prefix infix um, on the actual expression by first checking to see if it's a binary expression. And if it's a binary expression, then we can actually construct the left-hand side expression, the operation, and the right-hand side of the expression. Otherwise, we'll return the actual expression in prefix infix form. So this here is kind of the main thing that you'd want to look at for complex expressions, this list that's getting constructed. And then prefix infix is your recursive call that's going back to check to see if we've actually need to rewrite more of the expressions that you are traversing through. So it's taking effectively exp in this case is an expression tree. All right. For folks coming from other languages, it's an expression tree written in prefix form that you can end up rewriting into an infixed notation, where the infix notation rewrite is happening in the construction of this list. That's about it about this thing. It's a fairly straightforward thing. This is a slightly complicated extension of what we saw with ELIZA, but the techniques of actually running through and generating the actual equations is the same, which is we're using a rule-based translator. We grab the rule associated with the particular pattern that we're trying to match against, and then if that pattern is found, it will then end up using it for well, it'll end up substituting those unknowns into the special variables that we saw earlier here. The special variables, the question mark variables that we've encountered in our previous discussion of ELIZA. And then and only then do we run the actual solver. And the solver is doing a very basic constraint propagation solve. So let's see if there are any. Let's go through some of the problems now. Oh, before I start going through some of the other problems, let me show you a few more examples of this being used. So this is a contrived example that I constructed, but the book also gave a fairly interesting one. Let me see that I still have it here. Yeah. So this is, let me go to the beginning. If the number of customers times is twice the square of 20% of the number of advertisements that he run, um, and the number of advertisements 45, how many customers does Tom get? Notice specifically the call out to percentage here, because the percentage stuff is particularly interesting. Um, One thing to be aware of is to make it easier to parse, rather than trying to see that trying to instead of trying to split this has lexically, and then realize that the first part of this is an integer and the next part is a percentage sign. uh, a lot of the examples inside PAIP, and this is something I've noticed, explicitly does that ahead of time. And so this way, this structure becomes a very simple substitution, as you can see in line 53. This is just an example of the less than, but there is another one, 20% of of which rule is this running? This is here, 20% of. So it will actually go in and construct this um, to deal with the number of variables. So if we run this here, again, please note the commas are actually escaped. Um, we'll get the following equations that are going to be solved. So twice the number of 20 divided by 100 times environments. So it actually gets this construction here, and then um, and it gets it and it squares it accordingly, and then it then it uses constraint propagation to actually go and figure out the number of customers that need to be solved. Yeah, well, need to be given to Tom. This is an example of a fairly complicated, more complicated example than what I previously provided, mainly because of the structure of the equation that are being created. And again, it converted the square into something that can easily be understood. But this debugging of these rules it can now become natural for most people who have now encountered this enough times to actually go in and construct and see where the parser errors are actually happening, and then extend the rules database accordingly to actually handle it. But the equation solver doesn't change. We haven't actually touched anything in terms of actual implementation. And so, I mean, hopefully this makes sense to most people who've encountered this. So let's go through, let me just say one or two more brief things about this final thing. Just the one is the language analysis techniques that you just saw. Um, there really isn't any sophistication there, right? In fact, the rule-based translation of both ELIZA and this word problem solver is pretty much exactly the same. The same approach is actually created. But if you know that the types of problems and the types of questions that you're going to get is of a fixed type, like this one that we see in many algebra problems, then creating these kinds of systems becomes a fairly straightforward exercise. You just have to create rules to construct a system of equations from the natural language text, and then you can actually then run a basic simple constraint propagator to actually go and solve them for you. Um, and most importantly, for those of you who aren't, perfect English speakers and so forth, you really don't need to know very much linguistics to actually um, do the translation, which is very important because it makes the implementation very much simpler. Okay. And all right. So that's all I had in terms of presenting this particular piece. Um, I wanted to spend time in talking about some of these hard problems, but I haven't actually had a chance to really dig into them. So I don't want to spend too much time on solving these just yet until I have a chance to actually tackle them myself. So I will postpone our exercise sort of powwow to next week, just so this way um, I'll get some time to actually go and work through these problems in a little bit more detail. It took me a little while to understand what the hell solved equations was actually trying to do, and when it became apparent what the solve was actually attempting to do, I was like, oh, okay, I see what it's doing. This recursive call is actually generating the thing. The constraint propagation is actually leveraging the constraint propagation technique of just doing one at a time and then massive substitution. Um, I didn't get a chance to actually go and try some of these examples. So next week, we're going to be covering the exercises for Chapter 7. In the meantime, I do wish you all a happy holidays, and I hope you all will join me in our last episode of the year next week at 1 to 3 p.m. Uh, if one final thing. If you like our content, please do like and subscribe to our channel. So this way, Atlanta Functional Programming can provide you updates to the newest versions of our content. We normally run Common Lisp study group every Saturday from 1 to 3 p.m. And periodically during the week, we do offer talks on various topics, functional programming related. Um, if you have a talk topic that you would like to present on our channel, by all means, feel free to reach out to me. I am Bugram on Functional Programming Slack, as well as Bugram on the Lisp Discord server. Just DM me, and I'll try to get you scheduled. As usual, anybody who's in the Atlanta area, if you have a talk topic that you'd like us to schedule, by all means reach out to me as well on those venues too as well. And Tech 404, which is the Atlanta tech community's Slack workspace. Um, and we'll schedule your talk as soon as possible. So without further ado, happy holidays. And if I don't see you next week, I hope you all enjoy your New Year's too as well. I hope